Now let's look at this one. Now this one, we're going to go back and trace again the instruction, and we will see that transaction 2 is reading A, transaction 3 is writing A. That's again a conflicting step. It's the third conflicting step in the blue box, so this means 2 has to come before 3. We're going to go and scan it again, and we see that transaction 1 is reading B, transaction 2 is writing B, so that is again the third conflicting step in the blue box. So again, that implies that 1 needs to come before 2. So what we have found up till now is that 1 is before 2 and 2 is before 3. So this looks like, or if this is indeed what, we're not going to find any other conflicting steps, then this is basically this serializable schedule, or this schedule, it is serializable and it is conflict equivalent to the serial schedule where you run T1 followed by T2 followed by T3. You're going to get the same result. But wait a minute, I can also find this guy. Transaction 2 is reading B and transaction 1 is writing B. This is again the third step in the blue box. So this means 2 should come before 1. Now we have an issue. If you look actually to this one, there is a cycle there. And since we found a cycle, this schedule cannot be conflict equivalent to any serial schedule. Why? Because I am saying the following, according to the logic here. I am saying that the effect of this schedule is producing a result that is equivalent to, or which means it's really exactly as, T1 followed by T2 followed by T3, and as well T1 followed by T2 followed by T1 followed by T2 followed by T3, which is impossible. It cannot be both. Okay, once you have a cycle, you know that the result is not going to be consistent with any conflict, with any serial schedule, because again, I could deduce, I'm supposed to deduce from the graph which serial schedule this is producing an output that is similar to. Okay, the output here is going to be equivalent to one of the serial schedules if everything is okay. So saying T1 followed by T2 followed by T3, okay, yeah, sure, makes sense. But saying also this is equivalent to T1 followed by T2 and then following the blue edge, followed by T1 again, followed by T2 again, followed by T3, there is no serial schedule like that. So once I find a cycle, then this means this is a bad schedule. This is going to screw up my data in the database. And I'm just going to have to change things here. I cannot accept to run this schedule. And this is what the scheduler does. Okay? Now, I have here another example. You should trace it on your own. And this will be the precedence graph. And as you see, there is no cycles. What I just did here is that I just added more transactions. So we have 5 transactions. And I have put for you at the bottom of the screen the sequence of reads and writes that we are evaluating. And if you look at the blue box with the conflicting steps, you can actually build the graph. And as you see, there is no cycle. Consequently, this is conflict equivalent to one of the serial schedules. Now, this is the crux of the thing. How do we actually generate these conflict serializable schedules? Okay, what we are going to do is we're going to play with non-conflicting swaps or non-conflicting steps. Okay, let me show you an example. Now, if we start with a serial schedule and I keep making the swaps on adjacent non-conflicting steps, ultimately I must end up with a conflicting serializable schedule because I respected the conflicting steps and I didn't change their order. But I can, as long as I can find some non-conflicting steps, swapping them has no effect on the final result. So I will keep swapping them until I cannot do any further swaps. And the nice thing is, these swaps are conflict serializable. We'll make the schedule conflict serializable. Okay, I have here an example. So why are we explaining this now? Because this is actually how things run inside the scheduler. It will open the window for transactions to arrive. Let's say the window is 10 milliseconds. So within 10 milliseconds, let's say 2 SQL statements arrive. So it will accept the 2 SQL statements and will put one beside the other. Let's say T1 and T2. So it will put T1 and beside it T2. All the reads and writes of T1 followed by all the reads and writes of T2. And then it will go through all these reads and writes from right to left or left to right, swapping non-conflicting adjacent steps until there is no more swaps that can be done. And then it will run this schedule, which is for sure is conflict serializable. Would produce the result of T1 followed by T2. Or it could put T2 first followed by T1 and then make the swaps, which will produce the result of the schedule T2 followed by T1. Like the example I have here, transaction 2 is writing A and transaction 1 is reading B. They're completely unrelated, okay? This is non-conflicting steps, so I can swap them, okay? So when I swap them, I have now transaction 1 reading B first and then transaction 2 writing A. Okay, so this is an example of a swap. They have to be adjacent in order to do the swap. It's almost like bubble sort if you remember from CS3. They have to be adjacent. Now, I will show you here an example in reverse, because if what I'm saying is correct, if I start from any schedule and I keep reversing or swapping non-conflicting steps, I will end up with the serial schedule I started with. Okay, so let's do that. I identify non-conflicting steps. I have them in the blue box in the top right. I swap them. So I did one swap, and then I identify another pair, and then swap them. Identify another pair, swap them. Identify another pair, and swap them. Okay, another pair, and we're done. Now, if you go back to the previous slide, you will notice that the one at the bottom is a serial schedule. In fact, the way the scheduler works is opposite of what I have showed you in the previous slide. It works in reverse, from bottom to top. It opens a window, again, for incoming transactions. Let's say 3 of them arrive at the same instance. It will put the reads and writes, T1 first, followed by T2, followed by T3, or T3 first, followed by T2, followed by T1, and then we'll swap non-conflicting steps until there is no further things to swap. And then it will run this as a conflict serializable schedule. The part where we start using the precedence graph is when a transaction arrives next while these guys are being executed. So if only one transaction arrives and nothing else arrived within the window and these guys didn't finish yet, what the scheduler will do is we'll put T4 and then do the swaps again of non-conflicting steps, but before it continues running, it has to construct the precedence graph to make sure that what we are running now is conflict serializable. Because, okay, let me again dive here a bit, with an example. Let's say T1 had 10 instructions, reads and writes, and then T2 had 5 and T3 had 5. So in total, there were 20 reads and writes. We know after the non-conflicting swaps, the schedule is conflict serializable. And then they start running for a while. So instead of the 20, now we are remaining with 10. The 10 are partly T1, part from T2, and part from T3. Or instructions, reads and writes from T1, instructions, reads and writes from T2, instructions, reads and writes from T3. Now T4 arrives, we say, with 6 reads and writes. So the scheduler will put the 6 beside the 10, because the previous 10 are already gone. Okay, they have already been executed, the first 10. And now we have 16 of reads and writes. So it will do again swapping of non-conflicting steps, but it doesn't know now, because this is part of T1, part of T2, part of T3, and the whole of T4. It doesn't know is actually what it's looking at, or what it just made, is it conflict serializable or not. So it will go and construct the precedence graph to make sure that it is conflict serializable. And if it is, it will continue on running it. If it is not, it will postpone T4 till maybe T1 finishes and then put T4 again, do the swaps, and construct the precedence graph to see if actually this is conflict serializable or not. And ultimately, it will run T4. So Let's look at this takeaway. Starting from a serial schedule, repeatedly swapping non-conflicting steps until all such swaps are exhausted will result in a conflict serializable schedule. And this is a better schedule since it's more fair to all running transactions, as we've said before, instead of doing one at a time. What we look at now is how actually the scheduler enforces the serializable schedule. In other words, how does it actually ensures that a serializable schedule is running? So what I have been describing up to now is conceptually correct. What the scheduler does, it guarantees a specific sequence of interleaving of reads and writes to, number one, be fair to all running transactions, and number two, ensure that the final output is the equivalent of some serial schedule. But actually, it's not doing it the way I have been describing it. It's a little bit more complicated than that. The reason why it's a little bit more complicated than that, because if you notice in the beginning when I described what's inside a transaction, it's a sequence of reads and writes. Well, while I have been describing the scheduled output as a sequence of interleaved reads and writes. So the question is, are the reads and writes inside the transaction, or are they actually manipulated by the scheduler and outputted by the scheduler, as this illustration shows in front of you? And while conceptually it is correct that this is the effect that the scheduler is introducing into the running of these transactions, it is not exactly done this way that I have been describing. It's a little bit even more, involved than this. So let's move on, and then you will understand what do I mean by that. What the scheduler actually does is it has access to the transaction steps, the reads and writes, before the transaction begin to execute. So the effect of the scheduler working will be as if it is actually copying those into its own space. I mean the reads and writes of T1 here and the reads and writes of T2 here, and interleaving them properly according to what we have described earlier. But that doesn't really happen. The steps are still inside the transaction, and we need them, the reads and writes, to be inside the transaction, because as we've mentioned before, a transaction is running in its own thread. It's not actually running in the main thread of the database engine. It's a separate thread per transaction, and this enables concurrency, that we actually can run many SQL statements at the same time. So what actually the scheduler does, it will look inside the transaction to figure out the steps that this transaction is going to do, and it's going to do something to ensure that the final outcome is what we have been describing before, that the interleaving is correct. Okay, so what I have been putting as in the previous slide, logically it is correct, conceptually it is correct, it's the effect of what the scheduler does, but it's not doing it in the way I have been describing earlier, which is that this is the output of the transaction. It's actually the result of the actions of the scheduler that it will look like that it is actually interleaved properly. But the steps will remain within the transaction, running in the thread of the transaction. So let's take it step by step before I show you the real thing. What can we do to enforce serializable schedule? Very naive, unrealistic scenario is what I have here in front of you, which is run the system anyway, okay? And whatever happens, happens. And then record what's going on, the sequence of reads and writes, so interleave them anywhere you like. And then suddenly when you decide, oh, okay, let me check if this is actually a good execution, you find that, oh, it's not a good execution. How would you know it's not a good execution? You construct the precedence graph and you find that you have a cycle, so you undo. Obviously, all this is unacceptable, at least not in the age we are at, because we are way beyond doing something like this now. We can do better. Now, the option that you might think of as well is, as it says in 2.8 down there, you buffer the transactions during n seconds, you stop the DBMS, make the schedule, execute the schedule, and repeat. In other words, you would create a window and accept transactions during this window, And when the window elapses, when the time for the window passes, you start actually processing the transactions. That's why I say buffer the transaction. So when it arrives, if you are at the beginning of the window, you have to wait till the end of the time window. Maybe that window is 50 milliseconds or 100 milliseconds. When you finish the 100 milliseconds, now you go and ask, okay, who has currently arrived in the last 100 milliseconds? You get these guys, and you create a serial schedule and swap the non-conflicting steps, and anything that will arrive in the next 100 milliseconds will be buffered until you finish running the current ones. And then you open the window again and you wait for 100 milliseconds, buffering all the transactions that have been arriving. You close the window. Now let's process these guys, and anyone that comes while you're doing that, while these transactions are running, again, you just make them wait. Okay? Now, it's possible to design a system like that, but the problem is now this is not an interactive system. While you're actually executing the transactions, you're not running any other transaction. You're just accepting them and holding them in a place, in a queue or whatever, until you're ready to process them. Okay? Now, I've kind of mentioned this before, and I told you this is what the scheduler does, but this is not exactly what it does. It does also something else, which is that it will allow running of incoming transactions after the window, but it's just going to construct the presence graph to make sure that the running is okay. But just buffering and closing the window to execute, and then buffering and closing the window to execute, again, is not going to really be that exciting as a database engine, because that means I cannot use it to support, say, an e-commerce website. So when people are buying stuff, they cannot be told, oh, the database engine is busy because we're running now the last bunch of transactions that arrived to our system. It just doesn't make sense. Okay, so again, this is not good for interactive systems. So what does actually a scheduler do to guarantee serializability? What it does, it uses locks. Now, I know some of you are taking the operating system course and some are not. So let me explain locks in a very simple term. Now, if you're taking the operating system course, you know what a lock is. It's a software feature that is part of the operating system. You invoke it using a system call, and that will enable you to prevent access to a resource. The resource could be a file, could be a memory location, could be anything you'd like. But the point is, if you get a lock from the operating system on a resource, then you prevent anyone else from accessing it. Now, if you're not taking the operating system course, what I'm going to say is, think actually of a physical lock. If you have a cabinet or a drawer and you buy a lock and you put the lock on the drawer, no one else will be able to open the drawer because you got the key to the lock. That's the same idea here. It's the same way of thinking. If a transaction gets a lock on a resource, no one else is able to access this resource. This resource could be a table, could be a page of a table, or could be a row in a page in a table. So the lock granularity might change, but the idea is the same, which is if you get the lock, no one else can access it. Now, why do we do it this way? We would lock a resource to avoid corrupting the data. So if two transactions are writing to the same row, they might overwrite each other. Let's have this hypothetical scenario. Two transactions are updating the name. So maybe the name is Ahmed, and the one transaction will go in and will change the E to NA. The other transaction will go in and will change the D to a T. So initially it was written Ahmed, AHMED. Two transactions are running, and one of them will change the E, the A to an E, and the other one will change the D to a T. Okay, so it becomes Ahmed. Okay, now what you want to do is you want to make sure that every one of those two transactions, when it modifies the data, it's the only one modifying the data. Okay, you don't want both of them to modify the data at the same instance. Why? Well, let's go back to this Ahmed example, and let's say both of them are modifying the last letter. So one of them will change the D to a T, and the other one will change the D to something else. Okay? let's say, for example, it will change it to an X. Well, the two transactions, if you allow it, if you allow both of them to go into the data and make the same change, the change to the same letter, which is the last letter, at the same instance, the result of the change is unpredictable. Okay? So to protect from the data from simultaneous unwanted access, we would use an operating system feature called locks. The way it works is one will request the lock. If no one else has the lock on the resource, will get the lock, and it is the responsibility of this transaction when it's done to release the lock by calling an unlock function. While the first transaction has this lock on the resource, if a second transaction comes and tries to access this lock, it will be denied by the operating system. It's not going to cause an error. The transaction requesting the lock will be blocked, will be stopped until the lock is actually available. So this is the essence of locks in operating systems, and they are heavily used for many things, okay? This is how we protect, or the operating system protect your data from corruption, okay? So what actually happens by the scheduler is that it inserts locks after inspecting the steps in a transaction. It inserts them in certain locations in the sequence of steps of reads and writes inside a transaction. This is actually how it enforces serializability. It does not really extract the steps and arrange them as I have been describing it before. That was more of a conceptual explanation, but actually what really happens is it inserts these locks, these system calls or function calls basically inside or in between the reads and writes to get the behavior we have been describing early on, a conflict serializable schedule. Okay, and we will see exactly the impact of that shortly. So we will set some rules. First of all, we are talking about well-formed transactions, which means the insertion of the locking request and the unlocking, subsequent unlocking request or function call is done properly by the scheduler. So if a transaction I requests a lock on a resource, either it gets it or it gets blocked. If it gets it, it's going to release the lock after it's done with the resource. The P here stands for processing A. So before a transaction access A or process A or do something to A, it will request the lock for A. And when it's done with the processing of A, whatever it's doing, it will unlock the lock on A. Okay? So while this is happening, our second assumption is that the scheduler is doing the insertions correctly and the operating system is also respecting the locks. So if one transaction acquires a lock on a resource, no other transaction, which is denoted here by LJA, no other transaction will request a lock on A and get it. It might request it, but it will not get it because transaction I here has the lock on A. So let's see an example now with locks, these things that are inserted by the scheduler. So you see here a simple example, two transaction, the first one, T1, is reading A, adding 100 and writing it back, reading B, adding 100 and writing it back. Now the second transaction is reading A, multiplying A by 2, writing it back, reading B, multiplying it by 2 and writing it back. Now what you see here is a serial schedule, our gold standard. If we start with 25 and 25 and we are adding 100 to A and 100 to B and then multiplying by 2, then the 25 become 125, we multiply that by 2, so it's 250. So the output of running T1 followed by T2 is 250 and 250. This is also another gold standard, which is T2 followed by T1. Now if we do that, we multiply by 2 first, so the 25 become a 50, and then we add the 100 from in T1, so that's 150, 150. Okay? Now, both of them are acceptable. I've discussed this before. It doesn't really matter which one runs. Both of them are acceptable answers. It just happens to be that they are producing different output because the order of running is different, which is perfectly okay. Now let's add locks. Now, our first attempt to use locks, or if I'm introducing the way exactly it works, is in a kind of in 2 steps. So let's just do kind of naive locking scheme. So let's assume that our database engine scheduler, this is what it's going to do. It's going to insert these blue statements, or the instructions in blue. The rule is, before you use a resource, you lock it, and then when you're done, you unlock it. So you see now in transaction 1, I'm requesting the lock on A, and then I continue on to read A, add 100, write A, and then I unlock A. And then requesting the lock on B, I'm still in transaction 1, read B, add 100, write B, and then unlock B. Now in transaction 2, I do the same strategy. I will lock A first, and then unlock it when I'm done. So I will release the locks for anyone else to take it, and then I will lock B, I will do the processing of B, and then unlock B when I'm done for anyone else to take it. Okay, so basically, more or less, I would say this is what the scheduler is going to do. It's going to insert these locks. Okay. Now, let's look at these 2 transactions running now with the context switch happening as it's shown here. So, for some reason, the operating system decides to run the thread for T1 first. So we request the lock on A. No one else has locked A, so we get the lock. So we proceed by reading A, adding 100, writing A, and then unlocking. And then a context switch happens. So T1 thread is preempted, T2 thread is activated, context switch is happening, we put the T2 on the CPU, and now it starts running. So I request the lock on A, I read A, multiply it by 2, write A, and unlock A. I don't need it anymore, so I'm going to unlock it. This is the right kind of way of working with locks. And then I request the lock on B, read it, multiply it by 2, and then write it and unlock B. Since T2 thread will run from beginning to end, the operating system realizes that, knows now that T2 has stopped, so it will put T1 back on the CPU, doing a context switch and putting it on the CPU, and now T1 continues, locking B, reading B, adding 100, writing B, and unlocking B. Now, if you try to compute the values here, you will notice that we have an inconsistent state. The final result should either be 125, 150, 150, or 250, 250. Because either we add the 100 first, making the 25 125, and then we multiplied by 2 for both of them, so it's 250, 250, or that's the serial schedule T1 followed by T2, or we do T2 followed by T1, so we're going to multiply by 2 first, so the 25 becomes a 50, so 50 and 50, and then add 100, so it becomes 150, 150. What we are seeing here is an inconsistent state of 250 and 150. The reason why this happened, because if you look at T1, when it starts running, it updated the A by adding 100, but then the adding of the 100 to the B was postponed after T2 is running. So when T2 now, after the context switch, when T2 is running, it was multiplying by 2 the 125 in A case, because we've added 100 to A successfully, but we didn't have a chance to actually add the 100 to the B, because we were running T2 all from beginning to end, so we multiplied the 25 by 2, so it became a 50, and then when the context switch happened back again to T1, I added 100 to B to become 150. Okay, so locks are usable, but there is something we have to do here to make sure that we are getting a consistent state, which is again 250, 250, or 150, 150. And this is again to stress the point, A equal to 250, B equal to 150 is not the output of any serial schedule, either T1 followed by T2 or T2 followed by T1. So what we're going to do is what actually database engine schedulers do when they insert locks inside the transaction. They do it in a specific way called two-phase locking, which will solve our problem. Okay, so let's look at what is two-phase locking. Now, in two-phase locking, the way it works is that a transaction will request all the locks it needs before doing the first unlock to any of the resources it got a lock on. Okay, so again I will repeat that. It will do all the requests for locking resources before you see any unlock system call. So it goes like lock, 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 and you don't have any more locks to lock or locks to request. You got a stream of locks requests, and finally you start seeing, after you're done with the locks, you start seeing unlocking. So you go unlock, 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 unlock. Okay, so this is the same example we were looking at with two-phase locking. In transaction T1, this is what will be actually inserted. This is the real thing. This is what gets inserted by database schedulers. So in T1 you see a lock request inserted first. That's transaction 1 locking A, read A, add 100, write A, and then you request the lock for B that you're going to work on later on before you unlock A. The same story in T2. Okay, I will, if you look at T2 steps, I will request a lock on A, read A, multiply by 2, write A, and then request a lock on B before I unlock A. So again, two-phase locking means I'm going to go through two phases. The first phase, I request all the locks I will ever need. And in the second phase, I unlock all the locks I got that I ever needed. Now, let's try to trace this guy. So let's say that we have the following. T1 starts running first by the operating system. So the thread runs. I request a lock for A, which is L1A. It will get it. It will read A. It will add 100 to it. It will write A back. And then we'll request a lock on B. Since no one else got the lock on B, we're still running T1. We didn't run at all T2. It will get the lock on B. And then we will unlock A. Now, a context switch happens. Now T2 starts running. It will request the lock on A. It will get it because T1 just released the lock on A. We'll read A, multiplied by 2. We'll write A, and then it will request the lock on B. Now, what's actually going to happen here is that T1 already has the lock on B. Once the call to requesting the lock on B arrives to the operating system is maintaining a table of locks, and it will figure out that T1 already has the lock on B. So the request by T2 to get a lock on B will be denied. Basically, in terms of operating system behavior, T2 thread will be blocked because it's requesting a lock and it doesn't have the lock. Someone else has the lock, or it's requesting the lock and someone else has the lock. The lock is not in the operating system, it's with someone else. So it will be blocked. Once it's blocked, it will be preempted. It will be taken from the CPU and the context switch will happen again. Now, if we imagine that in our database engine there is nothing but these two transactions, so the context switch will happen to T1. That's the only option that is in there, which will enable T1 to continue running. So this actually is the way that the scheduler enforces serializability, by inserting two-phase locking or by using a two-phase locking mechanism, so that if an undesired context switch happens in a thread that is currently running that we wanted to run is preempted and another thread is activated and placed on the CPU, the two-phase locking will delay or basically block this thread, which means we go back to the one that was initially running, and then we are happy. We are actually getting the sequence of reads and writes that we want to be executed. Okay, so now the context switch happens after this T2 getting blocked, and T1 continues running and it will unlock B, and when it unlocks B, and this was the end of T1, the operating system will realize that T1 stopped, so it will context switch to 2, and this guy continues running, and we get a consistent state which is 250 and 250. Now, if you have been taking the operating system course and you have been following content, you should immediately by now be asking what about deadlocks? And obviously we have a problem here. Now a deadlock, it's called a deadlock because it's a deadlock. You know, you're deadlocked, which means you are in a situation where you cannot get rid of. This will happen, you know, in the following scenario. If you look at T1, it's requesting the lock on A, it's reading A, adding 100, writing A, it requests the lock on B. Now, what if it's at the same time T2 was running, request the lock on B, got it, read B, multiplied B by 2, it will write B, and then request the lock on A. Both of them will be delayed on each other or will be blocked waiting for each other. And obviously this is a problem. It doesn't show up in exactly this way if you're running on a single core CPU, but if you're running on a dual core CPU, just a piece of code in front of you here should cause a deadlock. Now, if you have been taking the operating system course, you know that there are techniques that we could use to detect deadlocks and basically roll back or stop one of these transactions to enable the other one to proceed, but I don't really cover it here in this course because it's beyond the scope of this course. But yes, we have a problem with deadlocks, and what you learned in the operating system course regarding the treatment of deadlocks or the detection of deadlocks and solving deadlocks is very much applicable here. So the takeaway, serializability is enforced in database engines using two-phase locking. That's the real thing. That's actually how the scheduler does it. Second takeaway, in two-phase locking, a transaction requests locks for all resources it needs access to before it releases any of those locks. And as I mentioned, we will assume that deadlocked transactions are rolled back. They will not appear in the schedule as if they are not running at all. But again, this is not really the scope of this course, so I'm skipping over it. And you will not get questions about deadlocked transactions in an exam, for example, because it's outside the scope of this course. Now, something very important about two-phase locking. Two-phase locking is great, two-phase locking works, but it is not a cheap thing to do. It is a very expensive actually operation to do in an operating system or using any operating system for that matter, because the behavior of two-phase locking means that if you get lots of transactions arriving at the same instance, let's say you got a very busy website and 50 users are logging in at the same instance pressing buy this item, okay? What you're going to get basically is a jump in the number of locks requested from the operating system. And locks are maintained, as I've kind of mentioned before, you know, that they are maintained inside the operating system and given to various programs or various software or various pieces of code when they request them. So this notion of a sudden rise in the lock requests is a little bit problematic from the operating system point of view. And you always have this pattern that's highlighted by this graph with two-phase locking, that you've got a growing phase when you have like a flood of SQL statements arriving at the same instance inside the database engine, and you got a shrinking phase when those transactions are actually finishing. The problem not really in the shrinking phase, the problem in the growing phase, that these are heavy resources inside the operating system. So if you suddenly get like 50 SQL statements at the same time, and on average each one of them is asking for 10 locks, then you are going to request 500 locks from the operating system within a very short duration of time, and that might delay things down and affect the performance of the database engine. So it's not something to be careless about. And really there is no simple way to solve this problem. It's a problem always that does exist with database engines, that they all use two-phase locking because of their advantage, but now you have a problem that they will slow things down or cripple things down if you get a huge number of transactions arriving at the same instance. Okay, so in the next part of this lecture, we're going to talk back again about two-phase locking, but from a different perspective, from the perspective of using SQL statements to define how you would like to run your transactions. So we'll talk about that later on. Now, Let's dig a little bit even deeper with locks. One of the problems with locks that we have used up till now is that they are blind to the activity we are actually doing. So whether you're doing a read or a write, we always requested a lock. But there is a huge difference between reads and writes. The really problematic ones are the writes, because when you write, you don't want anyone else to write with you while you're writing to a specific row. But if you are actually reading, then it's okay that you have n number of transactions reading even the same row. What's the problem there? They will all read, okay? So like you see here in this example, when transaction 1 is reading A and transaction 2 is reading A, well, both of them are reading, so we should allow this, because, I mean, what's the problem here? I mean, there's really no problem. Both of them are interested in the same piece of data. Let them read it. There is no issue that will, affect the consistency of the database here. Now, for that purpose, we have types of locks, okay? We have a shared lock if you are doing a read. Then what you should do is, or actually to be more exact, what the scheduler should do if the operating system supports the notion of shared locks as a feature in the operating system, it should request a shared lock on the resource. This is what you see down there. It says, transaction 1 is requesting a shared lock on A, transaction 1 reading A, transaction 2 is requesting a shared lock on A, it's reading A, and so on. And then it will unlock the shared lock and unlock the shared lock by the two transactions. Okay, so this is an enhancement to the notion of locks where we differentiate between reads and writes. Okay, so what if you're doing a write? Now, a write, well, is problematic. So if a transaction would like to write to a resource or to a row or to a page, it should request an exclusive lock. So that's the X that exists in this lecture slide. So if it says S, it means it's shared. If it's X, it means it's an exclusive lock. Only one is allowed. Okay. Now, what about if a transaction is doing both? Okay. So what you're seeing here is one option where transaction 1 will request an exclusive lock, and then we'll go and do the read and the write of the resource, of the row or the page or whatever, and then it will unlock. This is one option. Okay, because since you're doing a write, then you would request a lock anyway, so just request an exclusive lock and do the read under the exclusive lock or within the exclusive lock, and when you're done with the write, then unlock the exclusive lock. Now there is another option which some operating systems support, which is that you can upgrade the lock, and this is obviously a little bit more advanced as a lock feature. So what and again, this has to be supported by the operating system. It's not just a database engine issue. So here, transaction 1 will request a shared lock, and then we'll go to read the resource, and then when it's about to write to the resource, it will request an exclusive lock. And in this case, we describe this kind of behavior as an upgrade to the lock, going from shared to exclusive. Then it will do the write, which is transaction 1 writing A, and then it will unlock, and it will unlock, it's actually unlocking the exclusive or the upgraded lock. Okay. Now again here, the assumption is we have well-formed transactions, which mean that the insertion of these locking statements are done properly by the database engine scheduler. When it requests a shared lock, it will release it after the reading, and it will request an exclusive. That means we're going to do a write, and it will release it after as well. Okay? And the operating system is behaving correct along with the scheduler, which means that if a scheduler says that I would like to get this transaction access to this specific resource using a shared lock, then the operating system should never give another transaction an exclusive lock on that same resource. And but it's okay to give obviously a shared lock. And if a transaction requests an exclusive lock, no one else will get either an exclusive or shared, because this transaction is about to write and we don't want to corrupt the data. We usually express this as a compatibility matrix. So if a transaction has a shared lock, which is the S, other transaction can get a new request, can get another shared lock, but it cannot get an exclusive because you cannot read and write to the same resource at the same time. Otherwise, you might be reading corrupted data. Now, if a transaction requests an exclusive lock, no one else can get a shared lock or an exclusive lock. And this is kind of a summary of how the lock behaves. Now, in terms of two-phase locking, no change here. We are going to follow the same rule we described before, which is request all the locks before you do any unlock. We have also, as feature in certain operating systems, which is again an advanced feature, a different type of lock called the increment lock. And this is made specifically if you're doing numeric computation, specifically additions and subtractions. Okay, let's look at the chart at the bottom, or this example that starts with a equal to 5. Let's say two transactions are adding values to 5. This is very common in the database world when you have an auto increment column, or you have a numeric field, let's say your stock count of certain items, and usually all the updates you're going to do to this stock item is to add 1 or add 2 or add 5 and so on, or subtract 1, subtract 2, subtract 5 and so on. Now let's try to understand the rationale here before we see it actually or we talk more about this here. If you start with a equal to 5 and you get two transactions, one of them is adding 2 and the other one is adding 10. Okay, now if you run the one that adds the 2 first, now the 5 becomes a 7, and then you run the one that adds the 10, so you end up with 17. If you do the other way around, you run the one that adds the 10 first, so the 5 becomes 15, and then you run the second one, which is adding a 2, so again you reach to the same number. Why will you always reach to the same number? Because inside the CPU, the simplest kind of instruction that you can do is a numeric addition, or basically an addition, a summation, or you're adding a number to a number. That's the simplest thing you can do. If you remember from your computer organization or computer processors course, you know, the fetch decode cycle inside the CPU, in 3 clocks you can do an addition, or in 3 clocks you can do a subtraction. So increment locks were specifically made for this situation where you're working with numbers and you're doing additions and subtractions. The nice thing is that they can actually elevate the burden of handling too many locks by the operating system if you're just doing numeric computations like additions and subtractions. Okay, and by the way, this is only applicable to addition and subtraction, not any other numeric computation. Okay, so what the increment lock as a feature enables the operating system to do is to pass the let the steps pass to the CPU, because inside the CPU you can only do an addition or subtraction in 3 clocks, the fetch, decode, execute cycle, and you cannot do it in parallel inside the CPU. It has to be three clocks to get an addition. So whether you pick this one or that one, or whether the CPU picks this one, that addition, the I or the J, adding 2 or 10, it doesn't really matter, because in the next 3 CPU cycles, next 3 clock cycle, 3 clock ticks, doing another, fetch, decode, execute cycle, you're going to do the other addition. Okay. So again, this has to be supported by the operating system. Not all operating systems will have an increment lock. Okay, and it's a great feature because in many situations we have auto incremented IDs or ID as a column, and if the operating system supports increment lock, then the database engine scheduler will actually insert increment locks instead of just exclusive locks. So again, looking back at our compatibility matrix, if you look at the left, we have this, if already the transaction running has a shared lock, someone else, a new request, can take another shared lock on the resource, so both of them will be reading. No one else can take an exclusive, no one else can take an increment. Now, if someone takes an exclusive, no one else is going to take any other lock on that resource. However, if a transaction requests an increment lock, shared lock is not allowed, exclusive lock is not allowed, but other transactions requesting an increment lock will be allowed, because again, they will be handled at a lower layer inside the hardware of the CPU. So the takeaway, there are 3 types of locks used: shared, exclusive, and increment locks. Now we come to the almost last topic in this lecture, which is this notion of using a tree to maintain track of the locks that were allocated and to have some kind of granular control on what is being locked. Okay, so let's move on, and this will become clearer later on. What you're actually looking at here is a tree that represents the relation, which I'm calling R1, and below it there are children, 4 children, 1 for each one of the tuples. So this relation has only 4 rows. Now it becomes clearer soon. What actually, the way this works is as follows. Before I actually go into the material of this slide, let me tell you something, that one of the reasons why B+ trees are so popular in the database world is that they could actually be used, because of basically the way they are built, they could be used to track the locks that have been requested previously by other transactions working on the same relation, consequently using the same B+ tree. This is how it works. If you have a B+ tree built on a specific column and one or more transactions are querying the column that is used to build this B+ tree, the scheduler can use the B+ tree to understand what has been happening before and change the kind of lock that it was going to insert inside the body of the transaction based on working with the B+ tree. So let me read the rules, and in the next slide it will become clear. So we will always begin at the root of the tree, and if we are at the right element, we will request either shared or exclusive. If we're not yet at the right element based on the SQL that we are executing, we will just request what's called a warning lock, which starts with an I for intention. Okay, we have 2 types, intention to share and intention exclusive. Either we get it or we don't, and if we get it, we move down the tree. So let's look at an example. If transaction T1 would like to read the row T2 or the tuple T2, it starts from the root. Since it's not interested in the whole relation, it's interested only in T2, it will request an intention to share, which means it's going in, it's saying, I am going to later on request a shared lock. But I don't really need a shared lock on the whole relation. I need it on something that is way below in the tree. So it goes declaring its intention. Either it gets it or not. If it doesn't get it, it will be blocked and queued inside the node that has the label R1. If it gets it, it will move down. It will follow the reference down to T2. Now, if another transaction comes in and also is interested in reading, okay, but the whole relation, so it will request a shared lock right away, not an IS, not an intention, but a shared lock. This means it's going to read the whole thing, okay? So it will be allowed to do that. Now, if a transaction comes and is requesting, and it's going to write, but it's going to write to a specific row, which is T4, it doesn't try to get a lock on the whole relation, but it gets a lock on just T4 when it goes there, when it reaches there, when it traverses the tree down to T4. So when it starts at the root level, it will request an intention. It will declare an intention to request an exclusive later on. And since this is declaring an intention T2 and T1 was also declaring an intention at that level, it will be allowed. And then it moves to T4 and requests an exclusive on T4. Okay, so let's look at the compatibility matrix of all of this. So if a transaction currently holds an intention to share and a new requester that says requester up there requests an intention to share, it will be allowed. An intention to exclusive, it will be allowed, because this means it will request exclusive later on. A share right away, it will be allowed. An exclusive, it will not be allowed. So I just covered the first row here. Now the second row, if the current holder of the specific node we're looking at is having an intention exclusive, anyone that goes in with intention to share will be allowed, because this might request a shared lock on a different part of the tree than the holder, which have an intention exclusive, will request an exclusive lock later on. Like for example, the holder which has intention exclusive will request an exclusive on T2, while the requester, the new requester, is requesting an intention exclusive because it will request an intention shared because it will request intention shared on T5, which is different. Same thing for intention exclusive. However, requesting a shared, which means read the whole thing from the node you're at downward, is not allowed, because if someone already have intention exclusive, it means he's later on is going to request an exclusive. It means he's later on is going to write. So you cannot allow another transaction to read the whole thing while someone is writing part of it. And obviously exclusive is also not allowed. Now, if someone has a shared, other intention shared is okay, it's going to still read. Intention exclusive is not okay, shared is okay, exclusive is not okay. Someone has an exclusive, which is the last row here, no one else is allowed in, because this guy is going to write. Okay? Now, why is this interesting? This is very interesting because this is one of the reasons why B plus trees are used heavily, because we could implement all of this in a B plus tree, where we start from the root and we keep requesting the proper lock according to the current status of what was happening before, or what transactions went in before us, and consequently we could be blocked inside the B plus tree until the road is cleared, which means the transaction that was requesting the exclusive finishes. Then we can move on inside the B plus tree to read more values. But generally, even if you're not using a B plus tree, this is still used to track who is locking what and at what level is actually getting the exclusive lock. Okay? And what I have here is the rules which I have been describing earlier. So I'm just gonna leave this slide for you to read. Now let's see some exercises related to all of this. So this is now my example. Transaction T2 requests exclusive lock on R1. Yeah, no one else is in there anyway, so it will be allowed. And then it moves on to T2 and it requests an exclusive lock. And then it goes on to the first field in T2, the first column in the second row in the table, in the relation, and request an exclusive lock. Okay, so all of these obviously will be allowed because no one else is there. Let's say someone else comes, transaction T2 requesting this, and transaction 1 comes requesting an intention to exclusive. Sure, it's going to request exclusive later on, so it's allowed in. It also requests an exclusive, intention exclusive on T2, it will be allowed. And if it's actually going to write the second column in the same row, it will also be allowed, because it's a different column. Okay, so you see how granular can this go with this scheme of tracking the locks that transactions are requesting. Okay. Now, if transaction T3 comes in and it requests intention shared, it will be allowed according to our compatibility matrix. It will go to T2, will request intention shared, it will be allowed. When it attempts to read F2.2, which is the second column in the second row, it will be denied because transaction 1 is writing there the value. Okay. Now, this is an important part of understanding what can we lock. Obviously here this example is assuming something that's actually quite drastic, which is that we can actually have locks on the records, which means on a specific row in a specific column. And you might be asking, is actually this is how it's done? And my answer, it depends on the database engine. So not all database engine allows you to lock a specific record in a specific row. In fact, one of the things that people often criticized up till a few years back about MySQL. If you heard about this database engine, it's supposed to be the second most popular, actually it's the most popular open source database engine, but often coded as not the most sophisticated. It's just the most popular because it was always packaged with programming language environments. So people who used Perl web framework or Ruby, and all the Ruby on Rails stuff, or PHP. PHP is actually the one that made MySQL very popular. Basically, you download the environment for running PHP scripts, and you get MySQL with it installed. So there are, millions of websites running MySQL. In terms of sophistication, it's supposed to be the second most sophisticated after Postgres in the open source world. But actually, if you go and ask in MySQL forums, how you're doing the locking, and you will be surprised that up to like very recent, after a few years from, a few years back, MySQL only allowed locking tables, not even pages, tables, which means if a transaction is writing to a relation, the transaction would request an exclusive lock on the whole table. Even if the table has 1 million rows and they are divided into 10,000 pages, you lock the whole table to do a single insertion of a row. And it went like that for a huge period of time until they actually made it better, and now they have page level locking, so you can lock a page. What you're seeing in front of you here is we're doing record level locking, where we can lock a single record in a specific row. Okay, so that's way even more advanced, because that means you have this fine granular control, and this has to be reflected in how the scheduler works, that it will look at the SQL statement and understand, or basically the reads and writes, understand what are you actually writing, and it will just insert a log for the thing that you're modifying. So if you're modifying in a specific row the column H, it will just request a lock on H and not on the whole row. Okay, so this is the way more advanced version of things, and this is how Postgres does it. This is how SQL Server does it. So I'm going to skip this slide. This is how you actually do insert and delete. It's following the same logic, so I'm not really introducing any new material here. You have to get the lock to actually do anything. So insert and delete is just like read and write. So really there's nothing new here. So I'm going to move on to the last slide today, which is configuring the locks. So there are a number of parameters I want you to look at in this documentation that I have put for you here that describes how you can actually configure the locks. You have an amazing level of control because locks are very expensive in the database world. They actually can cripple down a database engine. So you have ability to set how many locks requested by different SQL statements that is coming to the database engine. Let's say you have a programmer who has no idea about the internals of a database engine. So he writes these horrible SQL statements that will end up, when executing, requesting tens or 20 locks or 50 locks in a single run of a SQL statement. So if you would like to control things, you can actually specify the maximum number of locks that a SQL statement can acquire, or a transaction can acquire through the scheduler. Or in other words, the maximum number of locks that a scheduler can insert inside the steps of a transaction. And this way, if someone sends to you a SQL statement that is complete horror, that is not allowed, it's haram to have such a SQL statement that spans 2 pages of SQL text, and that results in allocating 150 locks, for example. You could have control on that by setting a maximum on the number of locks allocated per SQL, per page, per table, per transaction, and so on. So you will identify developers who are not proficient in writing SQL, or are just sending you some garbage that slows down things. So you have lots of controls. You should check these pages. It will tell you a lot about configuring locks, because it's one of the advanced features that you have to be worried about. You should also be worried about the operating system you're running on, because say you're running on Windows, which is again I think is really a bad idea to run a database engine on Windows. Um, uh, well, on Windows actually we don't have a lot of control, but let's say you're running on an operating system that you know you're going to have heavy traffic to the database engine, and your strategy should be you need to check with the operating system, documentation, if you can actually change its locking procedure, or at least know about what kind of locks it supports. For example, if you look at the documentation of Linux, certain versions support increment locks, which are very, very important, because most of the time what we are doing with numeric columns is that we are incrementing and decrementing them. So having an increment lock is an amazing advantage from the operating system for you as a database engine developer. So you should check the features of the operating system. And sometimes, because of two-phase locking, you have to go to the operating system and modify its configuration to enable requesting lots of locks in a very short duration of time, because some operating systems, like for example Linux Ubuntu, will just throw an error if you request like 100 locks suddenly. Okay, so two-phase locking will not really work if you have lots of traffic to the database engine, because if you're running on Ubuntu, it won't really pass, won't really allow you to do many lock requests in a very short duration of time. It would suspect that you're trying to bring the system down. Okay, so you'll have to again look at the operating system and figure how to actually change the configuration. And these are the lecture slides, sorry, the pages that you need to read for this part of the course.